Okay, well, I'll say as I said this morning, because it was the start of the month and I didn't have the access code, I didn't have all of the computations and things like that, and I haven't really done anything today in the time allotted, but so all of the computations have been done by me in the last 24 hours, but I hope that they're illustrative. I'd like to thank the organizers of the conference and also my supervisor, Dennis Sipp, and my informal advisors, Peter Schmidt and Greg Pavliotis from Imperial College. Also one thing to say, in my abstract, it talked a lot about stochastic mathematics, but that was written for the first conference, and lots of the stochastic things didn't actually work very well in the non-self-adjoint case. So if we have time at the end of the 20 minutes, I can go through some of that on the blackboard, but if not, I'll just talk about the deterministic results. So just as an overview of the talk, we have the introduction, where I'll go over some mathematical description of fluid flows and amplitude equations in fluid mechanics. And then I'll talk about one of the ways we make amplitude in fluid mechanics, which is weakly nonlinear expansions, and how in the normal case we can get second-order expansions. And then I'll talk about some important concepts, and then I'll talk about how we can make good amplitude equations in fluid mechanics in the non-self-adjoint case. And lastly, in part 5 will be some conclusions and perspectives. So the mathematical description of open shear flows can be split into 3 categories. So we have linear stability analysis, and linear stability analysis is calculating the Jacobian of the linearized Navier-Stokes operator, and this is where we see at what parameter values do bifurcations occur and things like this. There's also the non-modal approach, which was developed by Peter Schmidt and other people, which is how sort of non-self-adjoint operators respond to perturbation, which is unexpected in the non-self-adjoint case. And most recently, there's been using the nonlinear modes, using the global modes, which were determined in the first part, and doing some nonlinear analysis with those via weakly nonlinear expansions. And these are sort of the 3 main historical categories. So only actually one of these tools takes into consideration the non-normality of the linear operator, and that's this one, the middle one. And therefore, in the middle one, we're actually able to find out the sort of characteristics at the flow at intermediate times. This tells us what happens at the beginning, this in the linear approximation, and so does this. But this actually tells us what happens in intermediate times. So let's have a look at the global modes and the amplitude equations now. So global modes and the amplitude equations that govern them are sort of 2 separate topics which have recently come together. So I'll talk about amplitude equations first, and then weakly nonlinear expansions. It's the recent way of making these amplitude equations. So Landau first described the development of a single fluid instability near its onset, and we recognize this as the Stewart-Landau equation, where A describes the complex amplitude of a coherent structure. This coherent structure in fluid mechanics would be called a global mode, but it would really be putting a modern vocabulary in the past to call this a global mode. And so this constant gamma is the distance from criticality, so it's either positive or negative. And this constant lambda 1 was sort of suggested by Landau, but was only really worked out computationally recently. So it was Stewart who worked it out for Poiseuille flow, and it was also calculated by Reynolds and Potter, Picaris and Scholler, and Davy calculated it for Couette flow. For flows with more complicated bifurcation characteristics, such as secondary instabilities or depending on different parameters, it's necessary to go into higher order in the amplitude equations. And there are some people who came up with new ways of making amplitude equations which did this. So we have the amplitude expansion method, which was by Watson and also by Hebert. And we also have the method of multiple scales. And Fujimura, in his 1989 paper, showed that the method of multiple scales and the amplitude expansion method are more or less equivalent in supercritical cases. And we also have normal form theory as well. Amplitude equations actually tend to be representative of the whole flow dynamics, including the saturation characteristics, not just the bifurcation characteristics in normal situations. And we'll give an example of this. So, in order to demonstrate how sort of amplitude equations work in the normal case and don't work in the non-normal case, we'll use this equation, which is non-self-adjoint because of this part here. And also, this is the real version. It's we call it the real non-self-adjoint Ginzburg-Landau equation. The complex equation has been used as an equation to demonstrate non-normality in fluid mechanics on several occasions. We also have this cubic non-linearity here. As this nu increases, the equation becomes more non-self-adjoint, and by this we mean that the direct and adjoint modes become further apart. However, because we have this term here, it always stays critical. So the eigenvectors are probabilist Hermite polynomials here with a sort of a shifted Gaussian. And these are just some constants from here. And we have the adjoint operator, which just has a plus here, and the minus shows up. So if you can see that the Gaussian is on the other side of the y-axis. And we normalize, so when they're integrated in the L2 product, we have a bi-orthonormal basis. And here we can see the adjoint and the direct eigenvalues respectively, with blue being the direct and orange being the adjoint. And for greater values of nu, they get further apart. And that's how we say it's becoming more non-normal. Also, we do the pseudospectra. I'll just say that I think this purple line is for like 10 to the minus 1 and 10 to the 0. So I'm not sure how relevant it is, but this is nu equals 0, nu equals 1, and nu equals 2. So we can see that the pseudospectra become sort of more important as the values of nu become higher. Also, sort of seeing the pseudospectra as places in which sort of the eigenvalues can move, we can see that this would make it more important that if we're using the eigenbasis as a basis, not to take a subsection of it. Also, here we see what is characteristic of non-self-adjoint operators is that we have a split between the computationally computed eigenvalues and the analytical eigenvalues, and which gets more drastic as the non-normality increases. So we derive our amplitude equations in a fairly standard way. And so first of all, we just put our equation on a dissipative time scale by rescaling tau equals epsilon t, and that should be u equals epsilon to the half v. And this is the equation on a dissipative time scale, and then we introduce the perturbation expansion. So at the first order, we get the global mode, and we have it as the spatial structure, which is the zeroth eigenvector, and C, which is an amplitude, which we want to work out. And then we have at the second order, we have the Friedholm alternative, which gives us this amplitude equation here, which we can recognize as the Stewart-Landau amplitude equation. And this is our lambda 1 constant. Is anyone trying to say anything? No?
So, Valentin, please could you mute your microphone?
Okay, so I'll continue. And this is just a fairly standard way to get the lambda1 constant, which was first numerically derived in the 1960s for the cylinder flow, but this is a much more simple example. So we put this back onto the original time scale, and then we have the first order approximation, which is this amplitude and this spatial structure, and together we call this the global mode. We also have some second order expansions where we have two time scales, and we expand as before. Just for the two time scales, we have tau1 equals epsilon t and tau2 equals epsilon squared t. Putting them into the equation and comparing times a like order, we have the global mode again. We have our first order amplitude equation. And then we have to get a representation of the first W1 in this approximation here. Now, this is where the self-adjointness really comes into consideration, because in the non-normal case, too, we do a separation of variables. So we let W1 equals C cubed W1 hat. And so that gets rid of the C cubed. But to invert this, because this is a singular operator, we have to have some kind of condition here. Now, because it is the normal case, we can say that all of the dynamics along the zeroth eigenvector is at the first order, or at the zeroth order. So nothing in the zeroth order is along here. So therefore, we can take, say, the inner product of W1 hat with E0 dagger, or E0, they are the same because we are in the normal case, is 0. We cannot necessarily make this assumption in the non-self-adjoint case. And that is why it's more difficult to get second-order amplitude equations in this case. So we put this back into the equation, sort of input the values for the amplitude dc over d tau1, and we get a value for partial c over partial tau2. This is what we've assumed, and then, as before, we just put it back onto the normal time scale, and then we get the second order amplitude equation here, where we have this new spatial structure, which I think I've gone back and forth with my notation, but the W's and V's should be the same thing. I'm very sorry about this. But we have W here, and this should be the zeroth eigenmode and the second spatial structure, which is W hat 1. And we compare these. So if so, this is the first order so A is the first order approximation, which is given by this one here, U app 1. So that's just the global mode. And the second order approximation has this spatial structure here. And we demonstrate how it's important, even in the normal case, to go to second order amplitude equations, because these graphs, C and D, are the solution to the PDE, taking away the approximation. So we have a sort of a residue here, but in the second order case, that pretty much goes away. And we can see this from the side as well. So we also do this sort of graph to show the importance of the different terms in the amplitude equation. And we see that the coefficients of the zeroth eigenvector, which is the zeroth eigenvector, so it's this B determined by this amplitude equation, and this B determined by this amplitude equation of lower order, actually does not make that much difference. So this term, the red and the green line, are quite close together. The second order approximation, and Q is the solution to our PDE here, but the second order approximation and Q overlap completely. But this V1 term, which is not the spatial component along the zeroth eigenvector, sort of makes up the difference here. So this term, which is the V1, makes up the difference here. Okay, and this is how it looks when we go to more non-normal. I said our parameter nu makes our equations more non-self-adjoint. So in the previous case, we had nu 0, so we're in the self-adjoint case. Here we had nu 1. We don't have second-order amplitude equations in this case because we do not know the dependence we cannot invert in the same way here. So we just have the first order amplitude equations, and we can see that it doesn't give a very good approximation. So this is the first order approximation. This is the solution of the PDE. Take away this approximation, and we still have quite a difference left over. And this is nu2. So for nu equals 2, we have our approximation. We have the PDE take away the approximation, and this is at the saturation time. And there's a big difference. So, and this is just the side view. So the green line is the difference, the blue line is the approximation, and the orange line is the solution to the PDE. And this is comparing the spatial view at time t equals, I think, 1750 seconds. So this is well into saturation. Now to understand what is actually happening, because what is the difference between the normal case and the non-normal case? Because the normal case tends to work quite well when making amplitude equations. And this is when we use some fluid mechanics vocabulary. So we make the difference between absolute and convective instabilities. So say there is an impulse at time t0. A flow is convectively unstable if the impulse just propagates out, like so. The flow is absolutely unstable as if the instability grows and does not propagate. And this is the domain of absolute instability. And we can see at this 0, it sort of stays near to the spatial domain as t increases, where here the impulse propagates away from where it starts from. The mechanism in a non-normal case is described as such. Firstly, in order for a global stability in the form of a bifurcation, there must be a spatial region of absolute instability first. So we must have something like this sort of case. A flow can be decomposed into an infinite sum of non-orthogonal eigenvalue-eigenvector pairs that are initially excited by the condition. So we can see this as an initial perturbation. If the flow is stable, then the real part of all of these eigenvalues is less than 0. However, the non-orthogonal superposition of these eigenvectors produces a wave packet that initially grows in time. So we're in this situation, we have our wave packet here, but it goes out of the region of absolute instability and just goes away, and we don't care anymore. But if it's unstable, then this wave packet when it's unstable, the unstable modes interacts with the wave packet. So when you have an unstable case, you have a global mode, and you have a wave packet from the non-orthogonal superposition of the excited states, which interact together. And that's why the amplitude equations underestimate the flow in the non-normal case. So a mathematical description needs to take the interaction of these different spatial structures into account. So we also have an example of Chomez to illustrate the wave packet, and this is a nice 2D example which I've just taken from his paper in 2005. So we have a simple operator, matrix operator like this, with where beta and alpha are a complex constants with positive real parts, but the system is still stable. And we let phi1 and phi2 be the direct eigenvalues of L, and lambda1 and lambda2 be the eigenvalues. We let phi1 and phi2 be the eigenvectors of the adjoint of L, and the direct and adjoint vectors form a B-orthogonal basis. But these have not been normalized. If we look at the initial condition, the solution for an initial condition, we see we have something like this, and if the inner product between phi1 and psi1 is small, which can be the case because the eigenvectors and the adjoint eigenvectors don't really overlap, then this can be the cause of transient growth, which can be problematic if the system is unstable anyway. And here is the depiction of transient growth. So we have an initial condition, which is phi2 minus phi1, and then we see how the initial condition grows. So how do we rectify this methodology? Well, we rectify it based on a method of Wishek and Lustenik. It's not the Wishek and Lustenik method, because that is something else, but it's in a paper by Wishek and Lustenik. And one of the key differences between what we do and what Vishik and Justinik do is we only use a spatial inner product, not a full inner product, so we can take out the amplitudes. And also we extend the work to the non-linear case as well, but this is not really that much of a difference. Their work would have worked for the non-linear case anyway. So we write our operator. So we have our operator again. We write it into the first part, and we write it into the epsilon perturbation, which has our time derivative, it has our nonlinear operator, and it has our small parameter delta. And we have this kind of problem now. So we have the same boundary conditions as before, and we introduce the expansion, but the difference between this expansion and the expansion we had last time is that we put our zeroth eigenvector along every part of the expansion. So this way, we do not say that in the next order we have to neglect what was in the sort of zeroth eigenvector. So we put in terms and we compare it like order. Again, we get the global mode. We get the amplitude equation, the Stewart-Landau amplitude equation, which gives the same lambda 1 value. And then we invert this, we get this matrix here, but we invert the singular matrix with the normalization condition, this one. But we don't really matter about this sort of U1 here, because we know that whatever is not in this U1, it will maybe be along the zeroth eigenvector. So in this way, all directions are covered. And then we go to the next order. At each order, we have a necessary and sufficient condition for a methodology, which looks a bit like this. It's a bit different at each order because it's nonlinear. And we use the Friedholm alternative to give, and that gives us this kind of ODE. We solve this ODE using an integrating factor. And this is where we make a little bit of an ad hoc approximation, because in the previous case, our linear approximation was correct. It was just at saturation things went wrong. So we work out this constant d by assuming that the linear approximation is still correct. So we kill all of the linear terms at this order. Hence d is this, to make sure there's nothing linear in gamma 1. And then we move on to the next term. So U2, which is, so we've worked out U1, we've worked out gamma 1, now we're on U2. And U2 doesn't separate variables so easily, so we have to put in a little bit of an ansatz like this. And for each of the parts in this, we integrate again with the condition here, expecting that everything which is not covered by this condition to be along the zeroth eigenvector. So with this, we change back. So with this, we get this kind of sort of second-order solution, which was our objective, because we could have second-order solutions in the normal case, but we wanted to know a way to do them rigorously in the non-normal case. This is gamma 1, but with b on the original time scale, and here we still have our Stewart-Landau amplitude equation. We also go to the next order with gamma 2, and this one I didn't actually solve the ODE, but I worked it out as at the saturation value instead. And there we have this. This is gamma 2 when B is saturated. And what is interesting is that we notice that, for instance, here, because the saturation value is given by this. So all logarithmic behavior which occurs in gamma 1 and gamma 2 disappears at saturation, which is kind of what we'd expect. So we have the approximation, which comes from the first order amplitude equation, which is just U is approximately the global mode. And we have the approximation, which comes from our this amplitude equation, our better approximation. And so this isn't really that illustrative in terms of a 3D plot, but we compare it, and I think I have put these the wrong way around, but this is the one for the second order amplitude equation, and this is the one for the first order amplitude equation. So the one for the second order amplitude equation is on the left, And you can see it's a much better approximation. Orange is the PDE, blue is the approximation, and green is the difference in between. And this is at the saturation value. T equals 1,750 seconds. Okay? And here we add some miscellaneous numerical results. And this is just to show, we choose, I think this is at the x-coordinate x equals 0. I used a Hermite discretization for all of the numerics. So this is x equals 0.212 or something, the closest to the origin I can get. And here we just see a difference between the first order approximation, second order approximation, and third order saturated solution, and the PDE. And you can tell when U is 0, normal case, really not that much difference. And also, this is V1 and V2, so the spatial structures in the higher order approximations, and there's not that much difference. Here we have a new increasing slightly, and we see that the second order approximation is kind of needed, and the third order approximation, even better, is needed to recreate the saturation of the PDE. Obviously, this will not be perfect everywhere in the spatial domain because I haven't done a 3D plot, but you can see the second and third order better approximates things. And again, the spatial structures of V1 and V2 are not that different. Here we have nu equals 0.8, again becoming more non-normal. We have to go to third order to get a good approximation. And here we can see that the spatial structures V1 and V2 are actually quite different. So this means that as the flow becomes more non-normal, we need to go higher order in amplitude to capture the different spatial structures in the flow which contribute to the overall amplitude and of the flow. So, and we've realized that for 1.2, even our third order approximation does not make it. But however, our perturbation expansion, we show in an upcoming paper, which will be hopefully on archive soon, that if I can just go back, this expansion converges in the Vishak and Lustenik paper in the linear case, and we can also find a value of epsilon, or choose a value of epsilon, such that this converges in our case as well. And I think I'm drawing towards the end now, and yep. And here's the last picture I decided to put in fluid mechanics. Everything is very much concerned about the global mode. What is the behavior of the zeroth eigenvector? But we see as in very non-normal situations, the zeroth eigenvector, in the sense that we look at, in the dotted lines, we're looking at the global mode contribution in the second order, and we're looking at the global mode contribution in the third order equation, which if I can just go back, sorry for all this backwards and forwards. So the dotted line in the second order case represents this, and in the earlier case just represents this. And we see that this is not representative of the actual, of the Ginzburg-Landau solution of the PDE at all. It's actually not the total story, which is quite interesting when you think about in fluid mechanics, there is so much emphasis on the global mode. And that is it. So some conclusions. We cannot assume that the behavior along the zeroth eigenvector, whether described by a linear mode or a nonlinear mode, where f denotes a nonlinear function, is fully representative of a non-normal system, in particular the saturation amplitude. For highly non-normal systems, second order or third order terms have differing spatial profiles and have stronger contributions. And also, we cannot make the assumption that the higher order behavior will be completely orthogonal to the global mode. So this is the assumption that we made in the normal case, and the overlapping of various eigenmodes must be taken into consideration. And this, I didn't really have much time to go into it, but you see I used this normalization here. From our numerical experiments, it doesn't actually matter if we use this normalization, which suggests that the basis of eigenvectors of the linear operator has actually quite nice properties in the sense that we can write the solution in it, which is not necessarily going to be the case in the non-self-adjoint operator. So that is it. Thank you for listening. Oh, sorry, perspectives. Can this methodology be applied when there is degeneracy of the eigenvalues? Open flows, the non-normality manifests in the eigenvectors and the adjoint eigenvectors getting further apart. In Poiseuille flow or Couette flow, at the bypass transition, we have a degeneracy of the eigenvalues. We have a degeneracy of the eigenvectors, rather. So our methodology needs to be adjusted. We found the radius of convergence recently, and this methodology can also be applied to the complex situation, which I would have shown had I been more prepared. And after this, the next step is cylinder flow. That's it. That's all I have to say.
Thank you. Questions? Biagio would like to ask a question, or just playing with the microphone?
No, it was the applause. It was it.
Okay. Okay, so you have a question. Great.
To all the questions. I am just curious about what is the type of physical models, what are the kind of physical phenomena you're trying to model with these equations? What is the physical background of this?
So the real Ginsberg-Landau equation has not been used to model anything as such. The complex Ginsberg-Landau equation has been related to cylinder flow in the first bifurcation from a cylinder flow, and this was in a paper by Rosso-Palouse and Mankiewicz. We think that if there is, we have a cavity which, like a sort of a rectangular pipe which opens into a bigger rectangular pipe, we will have switching behavior, and so this real Ginsberg-Landau equation, which has a pitchfork bifurcation, will be useful.
Okay, thank you.
Any other questions? Comments? I cannot resist to ask you what's the content of the next 4 pages.
I think that's all bibliography. There we go.
References.
Just references.
Okay, thank you. So if there are no questions, let's thank again.